Hello guys, and welcome back to another video. Today it's a special video. I told you a special video was coming because we're going to talk about an essay I've written about mathematics. And I wrote this essay for a competition, the JonnyMath essay competition, held annually and organized by this professor and the University of Oxford. And I wanted to take part in this competition. I submitted my essay, and this is the paper version of the essay because I wanted to have a printed version of it. And we're going to talk about my article, and here's the article, so we're going to talk about it. I'm particularly proud of what I've been capable of writing, so we're going to talk about it. But before talking about the article, I wanted to tell you that I've been waiting to record this video because I wanted the article published on the website. So if you want to read it, you can go to this website here. I'll show you the website. This is the JonnyMath website, and this is the showcase of the essays. So this is the group 1, group 2, and here in the third group that came out yesterday, if you click on it, this is the group 3 from essays 31 to 40, I guess, and the winners will be announced in August. And here are all the essays. You can download them, and you can also leave comments if you enjoy reading one of them. So it could be interesting to read some essays. And if you scroll down to the very bottom of the page, here's my essay, the Leibniz notation, the most powerful yet misunderstood derivative notation in mathematics. And here's my essay. You can download it and read it, and also leave comments. Okay, but now let's go back to the essay because it's interesting. So we're going to not read the entire essay together, but just some parts of the essay, just to know what is going on and what I wrote. So here's my essay. As you can see, here's the introduction, and we're all familiar with the concept of derivatives. Before starting, look at the title. As you can see, a YouTuber had to write this title because it's the most powerful yet misunderstood. It's a bit of a mystery on the title, but now let's go to the introduction. So we're all familiar with the concept of derivatives, and if this is not the case, there's no need to worry about it. We will cover everything we need to know about them in the subsequent chapter. Now, for those of you who are mainly familiar with derivatives, it has certainly happened that you have come across several different ways to denote them, because there are all sorts of notations. In fact, there are all sorts of notations in mathematics to represent the derivative of a function, as well as everything else in maths. For instance, one could come up with his own personal notation and may express the derivative of a function f of x as follows. And here's a bit of a funny notation I decided to write just to do something funny. And the derivative with respect to x of f of x. This notation is silly, so please guys don't use it. In fact, I wrote, of course, it looks messy and way too long to be efficient to write down on paper, so please don't use it. Instead, we could adopt some more compact and effective symbols, as the one mentioned below. And here's the common ways we use to represent derivatives. And they all mean the same because there's the same mathematical object, the derivative of f of x, with respect to the variable x. However, each might express or better outline a peculiarity of what taking the derivative of a function means. For example, the last three notations specify what variable we are differentiating with respect to, in this case x, and sometimes that's useful. While the first three don't, because it is implicitly stated that we are differentiating with respect to x, and Sometimes, especially in physics, we denote the first one, that is the Newton notation, to express the derivative with respect to spatial coordinates, so x, y, and z. In maths, it just means the derivative of a function. In fact, here I wrote that sometimes we need to specify the function, the variable we are differentiating with respect to, because if we have, for example, a function f of x, but x is a function of t, and we want to differentiate with respect to t using the chain rule, we need to specify it. So, despite these clearly important aspects of notations, there are other subtle ideas behind some of them which give rise to some essential properties of derivatives we weren't aware of. This is the case of the so-called Leibniz notation, the df over dx symbols we saw earlier, which not only makes a lot of properties of derivatives more intuitive, but also led to the development of a new powerful branch of mathematics, and we all know what that is: calculus. By the end of this essay, you will hopefully have a broad picture of where this symbol comes from and how it has affected our intuitions in calculus, most of the time turning difficult tasks in more intuitive ones, and how it has driven mathematicians crazy because of the difficulty of defining things rigorously. At this point, we are ready to dive into this incredible journey across the history of calculus and, in the meantime, clarify every single subtlety underlining the mysteries and powers of this notation. And remember, don't be scared of all the technicalities discussed above, because we are going to learn everything step by step in an intuitive way. All of this introduction was needed as an injection of curiosity to let us embark on this breathtaking adventure. As always, before getting into the most enthusiastic part, we shall first review the basics. Okay, now I read the entire introduction just to give you a taste of what the article is all about. And if you want to read it, you can download it, obviously, but we're going to take a look at the entire article because it's 18 pages long. So, yeah, it takes some time to read it, but the introduction was needed just to, share with you why I decided to write the article about the Leibniz notation. In particular, sometimes when you solve first order differential equations, you just take the x to the other side and you treat df over by dx as a fraction, not a fraction, a ratio, let's say, and you do those multiplications. So I wanted to, to explain why, and why it can be considered a ratio and why it shouldn't be considered a ratio. And yes, because I've always been, scared of those differentials, and I always thought, why you treat df by dx as a ratio while it's just basically telling you that you're differentiating a function that has nothing to do with the ratio. Or yeah, sometimes it seems like a ratio. So this is what I wanted to talk about, and how mathematicians fixed the issue and wrote it and define it seriously, so, and rigorously, obviously. So we first, because this is aimed to a non-specialist audience, so everyone can read these articles. This is basically the second, but it's the first and main chapter of the paper, and apart from the conclusion at the end. And this is a bit of the history behind calculus and derivatives. So a common way to introduce this topic would be to throw a bunch of definitions and then deduce their properties while giving a reason for their importance, but this is not how things are discovered in maths. The definitions we see on our textbook come from the need of making some intuitions rigorous, not the other way around. And this is the whole point of this article. So we're going to talk about derivatives, why they were first invented, because of the two separate problems, the tangent line problem and the problem on defining instantaneous changes, for example, velocity. In fact, the other was to study the motion of bodies. The two questions were the main interest of two mathematicians and well, yes, let's say mathematicians, and also we all know Newton, the famous physicist. So the first one was Leibniz and the second Newton. Leibniz was interested in the first question, so the tangent line problem, and Newton was interested in the motion of bodies. So defining the tangent to a curve. So let's talk about the tangent. Defining the tangent to a curve was a problem that goes back to the ancient Greek times. They knew how to define the tangent to the conics, so the curves that comes from slicing a cone. So they are the circumference, basically the circumference, the ellipse, the parabola, and the I said three of them. Yes, and the hyperbola. These are the curves they were interested in. They knew how to find the tangent to these curves because the line that intersects these curves in only one point is the tangent. So there's no way a line that intersects these curves in one point is not the tangent. So it was fairly easy. They managed to do that. But when it came to more difficult and more exotic curves, they weren't able to do that. So they needed to find a new way to do that, to define them, and to find these tangents. The equation of a tangent is the slope, etc. Now, the other problem was the rate of change of position, that is called velocity, and in ancient Greek times there were all sorts of paradoxes arising from velocity because it wasn't defined what velocity was. Only on average velocity was defined, but for example, here's the Achilles, and this is one paradox arising from that. Okay, so now let's go here. So what are derivatives? Are simply a way of expressing the rate of change of some quantity that depends on some other quantity. It is needed to answer the question, how does a change in something affect another thing? And here's a function I considered, and here's a fun fact. Look at this function here, this wobbly function. This is a function that has an analytical equation. So, and I find it using GeoGebra, and as you can see, this space is written in kilometers, and this is the time to cover this distance. So distance covered as a function of time, and to keep things funny, I basically told that this is the space covered by a drunk cyclist, I guess. I don't remember. Oh, probably a cyclist. I don't remember. And he was a bit drunk, so he was constantly accelerating, then braking, and all of that. So as you can see, this curve is a bit wobbly, and it took me quite some time to do that, because what's the speed of this bike? It's the slope of the tangent line to a point. And if you find this slope, and I did it to draw it later, I show you, the speed is, a speed of 30, 40, 50 kilometers per hour. So it's also something not out of the ordinary, something, realistic. So, it's cool. It's a fun fact I didn't write in the article, of course, but you know it now. Um, Here we can see the straight line, because we know that the slope of a straight line is constant, because it's constant. You kind of climb on a straight line on a steep road that is not wobbly, or it doesn't have crest or trough. It's just constantly slope. So here we define what the gradient is. That is the ratio of delta y and delta x. So you all know that. We find that the ratio is equal. We confirm that looking at the ratio at different points on this curve. We compute everything. We find and to see whether this is indeed the gradient, what we do is that if we take a steep line, the gradient has to be greater, because the gradient is greater, obviously. So I confirmed it here. But now, what can we do on this function here? Well, if I'd ask you to grab a pencil and trace the tangent line to a point P on the graph, you might draw something like this. And this is what you do if I tell you to trace down the tangent line. And here's the tangent line. But how can we find that equation? So we basically take the point a little bit on the right of t0, and then we shrink these distances, this delta t and delta s. We bring the 2 points together, so the 2 points on the function come together, and we can define in the limit, we'll know the derivative at that point of the function, and that is nothing too crazy. Here I use Peter just to keep the example a little bit less abstract if you want to. So we shrink the two intervals and we get this. Now, this is not the definition of derivatives, because you know what's missing here. The limit is missing. But Leibniz didn't know about limits. We consider these insignificantly small deltas remarkably special. Introduce a special notation for them. Instead of denoting the infinitesimal change with delta, use d instead, which is called differential. Why d? Because it's a small delta, I guess, I don't know. So there's no limit. And this is the Leibniz notation definition of derivatives. Now, you may feel slightly confused by the idea of these small deltas. In what sense are they small? How can we quantify the fact they're small? In fact, even Leibniz was confused, because you cannot divide by 0. And those numbers are not 0, in fact. But if we try to take the derivative of function, for example, x squared, at the end we get 2x plus delta x, and then obviously dx has to be a non-zero number because we divided by it, we simplified it, so it cannot be 0, but then we put it equal to 0, and that's weird, isn't it? In fact, this worked, and this is why they kept using this definition. But Weierstrass was driven crazy by this idea. So in fact, he wrote he surely didn't say that, but I wrote, how the hell does a non-zero number exist? And this is true. It's something weird. And well, it seems he was right, so he decided to abandon the concept of differential, so these tiny changes, and he defined derivatives with a new tool just been added, or better, made perfectly rigorous, to calculus in the 1821 in Bontemps and Auguste Louis Cauchy. This new item were limits. So thanks to limits, we're now able to justify that cancellation of h, because that's a limiting process. So you get closer and closer. No matter how close you get, the limiting value is the derivative. And now we are obviously we have a nice definition of derivatives. They introduced this notation. This is the Newton's notation, so they just took this notation or used different notation, but they wanted to get rid of that ratio. But then the Leibniz notation came again into play. Just d by dx means take the derivative of whatever is written here next to the d in the denominator, so just a notation that means derivatives, not a ratio. But again, there are some useful properties. For example, the chain rule. As you can see here, this is the chain rule. If f is a function of u that is a function of x, its derivative with respect to x is df by du times du by dx. But as you can see, this seems like a lot as a ratio, because you can multiply and divide by du, you rearrange the ratio, and you get the following quantity. Then you can prove it from the limit, and you will find that this is indeed true. But it's a lot more straightforward to start from the Leibniz notation, and most of the time to prove something you first need to find that something. So you can even go and prove it, and it's fine, you have to do it, but it's simpler to just find it at first without proving it using the Leibniz notation, and it works. Also, this dy by dx times dx by dy equals 1, as if we were to cancel, just eliminate those dx's and dy's. And there are all sorts of properties of derivatives that seems like ratios, and this is why we keep this notation. Then I wrote this is something that mathematicians consider an abuse of notation, even though I didn't write it here, otherwise the article would have been way too long. But we can define this ty as the differential, so the linear increment of the function, but let's keep this for now. And here it comes another interesting part of the article, because this is something happened recently in 1960 compared to Newton and Leibniz. That was a bit, I guess in basically medieval time. No, after that kind of. I don't remember. Let me check. Okay, Newton was born in 1726. So yeah, that time. So it was a bit early compared to more modern times, like what I'm going to talk about right now. And let me switch camera. Okay, perfect. Okay, so you wanted, because the idea of infinitely small or infinitesimal quantities seems to appeal naturally to our intuition. This is something he wrote personally. Abram Robinson, he was a mathematician in the United States, even though he was born in another country, I don't remember what country, and he introduced hyperreal numbers. So there are two types of hyperreals. The conventional numbers, so real numbers, give rise to other hyperreals. Infinitesimals, smaller than any other known number, and their reciprocal, so 1 over the infinitesimal, is a number bigger than any real number, so kind of infinity. This is how we defined it. Obviously, there are all sorts of complications I didn't write, firstly because I don't know about them, and secondly because it's way too complicated for this article and for a non-specialist audience. But he defined the derivatives as a ratio, this time of these infinitesimals, but the standard function of it. What is the standard function? I also wrote it. When you have a complex number, you can take its real value, the real part of it, and the imaginary part of it, using RE and IM, those two basically functions or just notions to identify the imaginary part and the real part of that complex number. The same thing is here. You basically take the real part of this number with the standard function. So we have 2x, the real part, plus dx, the hyperreal part. No, hyperreal numbers is 2x plus delta plus dx. You just take the real value of it. So this is 2x. And this is the entire article. Obviously, I couldn't explain it to you entirely because in detail, because it's 18 pages long, this article. But I said at the beginning, if you want to read it, please feel free to download it from the Tom Rocks Maths essay competition website. And here's the conclusion. I just wanted to, just summarize what we've been talking about, and at the end, why derivatives are important, because they're used in every law of physics, and that sometimes there's no need to worry if we don't understand something in maths, because even the greatest minds struggled to define these concepts and get their head around those concepts. So yeah, this is what we have to learn from all of this. Now that's the end of the video. If you enjoyed it, please leave a thumbs up, share it with your friends, and please leave a comment also on the Tom Rocks Maths website, because it would be nice. So this is the website. Here's my article. So if you can, please leave a comment and subscribe to my channel. As always, until next time, bye.